And away we go. This is my video log for week 3 of my independent study. On the syllabus for this week, I was to add functionality to Gunship so that you can retrieve systems at runtime, and then also to add functionality to be able to disable and then re-enable systems, which would allow you to implement stuff like pausing in the game. If we open up an example of that, you can see we've got the create destroy test that I've been using for benchmarking right now. And if I hit the spacebar, that actually disables the system that's running that benchmark. So you can see that now it's no longer updating. If we actually look at our scene update time, it drops down to a hundredth of a millisecond when it's not running. But if we turn it back on, it goes up to 5 milliseconds. So that's obviously working just fine. If we take a look at the code that's making that happen, and we go into level manager system.cpp. This was previously performing the create destroy test. I moved that over into create destroy system.cpp. So now create destroy system is in charge of every frame creating some number of entities and destroying some number of entities. So those are those cubes that you see on the screen. In a level manager system, we just check if you've pressed the space key, and if you have, we get the behaviors manager. Behaviors in Gunship are what I refer to. Behavior is the term I use to refer to user-defined systems. So Gunship has a delineation between the built-in systems and user-defined like game behaviors. And then from the behavior system or the behavior manager, we retrieve the create destroy system, and then we simply toggle its active flag. And if we go to entity system.h, you can see that I've added this into system base, which is the class that all systems have to inherit from. I've added this active flag. Then we go to system manager.h in the update all method, which gets called every frame. It iterates over all of the systems, and if the system is active, it updates the system, which performs the whatever behavior it does every frame. This right here, this having the system itself track whether or not it's active, that's a very object-oriented approach to the problem. That's runs a bit counter to how I've been doing things within Gunship. The more, I would say, data-oriented, quote-unquote, approach to the problem is what I tried initially, which is within the array of systems. We've got this systems. This is a standard vector of systems. What you could do is you could segregate it into two parts. If we do a little ASCII diagram, you can segregate that into two parts, where the first part are all of the active systems, and then the second part is all of the inactive systems. And then when you want to deactivate the system, say you want to deactivate this one, what you would do is you would swap it in the array. So if we make this one plus and this one equals, no, we make this one plus and this one equals. So say we want to deactivate the equals system. All you do is you swap it in the array with the last active system. So make this one plus and this one equals, and then you decrease the count on the active systems. So we move that little bar there, and now this system is active, or is disabled, but we didn't have to change any data. All we did was we moved some data around, and that would save on the cost of having this active flag. So say we have 10,000 of these systems, and each of them has its own active flag. That's 10,000 bytes that we save. That's 10 megabytes. It also means that we don't have to perform in update all. We don't have to perform this check, system active, and this is a kind of a worst case scenario for branch mispredictions. There's no telling in advance, and there's no consistent answer as to whether or not this the given any system is active. So the branch prediction unit on your processor isn't going to be able to help you with this. So this is just going to be a hotspot for branch mispredictions. And again, if we had 10,000 systems running every frame, then being able to only iterate over the active systems and not have to perform that check of is the given system active would save a lot on processing time. However, and this is a trick that I'm using within the component manager. This is effectively the same trick that I use when I in the pooled component manager. Inactive components are swapped into this back portion that are of the inactive components, and then when I want to activate one, I just move that line of which ones are active and inactive, and up and now equal is active again. And that's useful for components because I expect to have tens of thousands or hundreds of thousands of components. For example, with the transform component, which uses the pooled component manager, almost every single object in the scene will have a transform component. Anything that needs to be rendered needs to have a transform component. The only thing that's not going to have a transform are managers, which just do some kind of processing. Everything else is going to have a transform component, which means we could have tens of thousands, perhaps upwards of 100,000 transform components. So saving on this kind of processing is incredibly valuable. For systems, I expect to have 100, maybe a couple hundred. 1,000 is just an absolute upper limit on how many systems I could ever imagine having. Because a system in Gunship is something that needs to happen every frame. It's equivalent to the update function in any game object within P2 or a more traditional game engine setup. So having 1,000 different types of game objects that each need their own update method is pretty crazy. Like that's probably pretty big for even a AAA level of game. And even if it's not, it's still not going up to tens of thousands or hundreds of thousands of different objects or different types of objects. So I expect the systems to be a far smaller collection. I expect to only have a couple hundred tops. So having this active flag is much less of an issue because I'm doing far less processing with it every frame. And it has the advantage of being able to do nice things like this, where I can simply toggle that flag, and it's really easy to toggle that value back and forth. Whereas if I weren't storing this value internally to the system itself, I would have to do something like if scene.behaviors.is active create destroy system, then set the create destroy system to inactive, else set it just to active, and then that code is a bit uglier. It's not that big of a deal, but it's it's more processing that you need to do. It's possible that I'm wrong about how many systems are in the game, or perhaps how big of a bottleneck this will be. If either in terms of the branch mispredictions or in terms of having this flag inside of the system base, it turns out to be more costly than I anticipated. It'll be pretty easy to implement this segregated array system for doing the disabled systems. But for the time being, I don't expect that to be a problem. Now, as far as things that I am So that only took a little while. That was a relatively simple change. So now, as far as what I did for the rest of the week, it was more profiling comparisons of P2 versus Gunship. Um, for the most part, the bottlenecks that I was cleaning up within Gunship came down to two things. It came down to uh, how my handling of Ogre resources and my usage of STL containers. Since Ogre is a very integral part of Gunship, it handles all of the rendering. It handles the scene graph. It handles loading meshes from the scene, and it's got its own material system for creating materials for rendering. Ogre is integral to Gunship, and it's how I handle it. It's got its own quirks of how it needs to be, how its resources need to be treated for optimum efficiency. So and there were just things that I was doing with how I was handling Ogre resources that were leading to bottlenecks, and it took some tweaking and playing around with to get those sorted out. But I seem to be at a point where it's about optimal. That leads that and that took maybe like 30% of the processing time out. After that was done, um, profiling was revealing that a huge chunk of my scene update time was happening within the STL containers, especially the hash maps or STD unordered set or unordered map. Um, the time to hash to erase elements from the maps was just crazy high. And that seemed really strange to me because in most of my cases, so if we were to, for example, pull up like let's say our mesh component, things that I was using these maps for, so we got like unordered map. Things I was using the maps for was like the indices. So I would be using the entity ID as the key, and the value would be the index into the meshes array, and that was just used for faster than linear time lookup of components. So inside your inside the get method, so if you wanted to like retrieve a reference to the component that an entity has, I was using that for faster lookups, and it wound up being a huge bottleneck, which kind of defeated the purpose. But since the key to the map was an entity ID, which is already an integer value, it seemed to me like the hash map process should be very lightweight, or at least I should be able to implement it in a way that's very lightweight. And I know that the STL containers can't necessarily do that, because they're designed to be very robust. They're designed to be used in a lot of cases, a lot of very different cases. Whereas I know my particular use case, I didn't need something so robust. I only need something very lightweight. So to address that bottleneck, I introduced a few custom container types. The first of which being entity map. If we go to entity map, we can see entity map is a hash map, a hash map table, meant to be roughly equivalent to STD unordered map. But it's specifically designed around the knowledge that I'm using entity IDs as the key value. So the key value isn't templated. It's templated over or it's not templated over the key type. It's templated over the value type. And that's allowing me to perform very fast lookups and insertions into the map. Currently, this map does everything that I need it to for all of my use cases so far. I can insert values into the map. I can retrieve values. I can remove elements from the map, and I can check if the map contains an element. And most importantly, the map automatically resizes itself once it reaches a certain capacity or a certain load level, which means that for the case, since one of the core parts of this create destroy test that I've been running is I keep ratcheting up these values of cubes per frame and total cubes, then this keeps going up this goes all the way from 1 to 10,000. If the hash map didn't resize itself automatically, I'd have to go in to every place it's being used and make sure it was being initialized with enough space for all of the elements that are being created. But I do have working resizing on the map, and it seems to be working just fine. I don't run into any errors. Um, and this custom container sped things up a lot. Enough that I started revealing other places where the STL was causing problems. So I also introduced entity set, which is a hash table like entity map, but it's just a hash set, so it just tracks unique values. And this is using tracking unique entity values, and this is used by the entity manager. If we go to entitymanager.h, we'll see that it's using an entity set to track which are the live entities. And this is used for things like checking if an entity is alive, or when we destroy an entity, we first check if if we don't try to destroy an entity that's not alive. And so that sped that up a lot. And once I got the hash set and the hash map out of the way, I found that the vectors also were a source of problem. And that led me to add fast array. And fast array is a dynamically sized array similar to vector, but it's optimized for plain old data types. So stuff. Basically any type that's safe to memcopy, this will work for. If the type holds onto a pointer into memory that needs to be holds some memory that needs to be freed after the object's deleted. So say if we're a string type, or if we're holding a resource to a file that needed to be a file handle that needed to be closed after the object's destroyed. This wouldn't work, because if we take a look at what I'm doing when I pop an element off of it, or if we clear it, when I clear the entire thing, the entire array, I don't actually call the destructors on all of the objects. I just set the count to 0. And that's fine if the array is over just an array of ints or an array of pointers, something like that, where I don't worry about calling destructors or calling move constructors and stuff like that. But any type that has those requirements, this won't work for fast array. So in those cases, I'm still using standard vector. And you see that again here when I reallocate. I'm just using memcopy. So when I need to increase the size of this array, I allocate myself a new buffer that's twice as large as the old one, and then I memcopy the old buffer into the new buffer, and that's very fast as compared to what standard vector is doing, because vector has to be much more robust. I'm using this because I know it's much more lightweight, and I know it works for my particular use cases. And with those containers in there, I've got Gunship is running much faster now. I pulled out pretty much the majority of the bottlenecks in Gunship, and we can actually take a look here. I've got this spreadsheet going that's got the data that I've measured on the update times, and this is for the create destroy test. And as I add more tests, I'll add to this spreadsheet. But this is for the create destroy test. So the way the create destroy test works is there are two variables that I can tweak. One is how many cubes are created and destroyed every frame, and the other is how many cubes remain every frame after the creations and destructions happen. Cubes per frame goes from 1 cube being created and destroyed per frame, which is just representative of a very static scene, very little changes every frame in terms of like nothing's being added or removed. Going all the way up to 1,000 items are being added and removed every frame, which is something like a big arena shooter, and everybody's firing their automatic weapons at full speed every frame, and their bullets being created everywhere, and explosions and bombs and stuff going off all over the place. Something very hectic like that. And then total cubes. That's how many cubes are staying put in the scene every frame. That ranges from 1 to 1,000, or 1 to 10,000 actually. 1 being a completely trivial case. No game only has just one object in the scene at a time. So that's just for testing purposes. Ranging all the way up to 10,000 objects in the scene at a time. That's like a very large level, almost AAA level of scene complexity. Just tons of objects in the scene, lots of detail, lots of things that need to be processed every frame. A week ago on the 12th, I ran these tests with Gunship, with both P2 and Gunship. I didn't have the 10,000 level up, so it only goes up through 1,000 for both of them. But we can look at the graph of both of those. And here the blue line is P2, the red line is Gunship. And lower is better, because this is the time in milliseconds for scene update. And this is graphed logarithmically, so it goes 0.1, 1, 10, 100. And that's done so that you can also see the differences here at the low levels. Otherwise, these differences would just completely trump it. But you can see a week ago, P2 was handily outperforming Gunship. At some of these peaks here. With one item in the scene and creating and destroying 1,000 a frame, P2 took 60 milliseconds to update the scene, which isn't very good. That's still like that's not even 30 frames a second, but it's still way better than Gunship, which was 167 milliseconds, which would be like 10 frames a second, less than 10 frames a second, like 7 frames a second. And actually, you'll notice here as we get out to having 1,000 objects static in the scene, the numbers get much closer. And actually, if I had continued this out to 10,000, I discovered later that once you have 10,000 static like items in the scene that stay every frame, Gunship starts to outperform P2. But they were both performing so poorly that it wouldn't even matter. They'd both be unplayable at that point. So it was kind of a moot point. Today, after making optimizations to both of them, after making heavy optimizations to both of them, we've got the same blue line here as P2, red line is Gunship. Gunship is now outperforming P2, but they're both much better. So at the trivial level, with one item staying put in the scene and 1,000 items being destroyed every frame, P2 is at 25 milliseconds. So that gets you pretty close to 30 frames a second, not including frame time. Gunship is at 11 milliseconds, which is if the render time is reasonably fast, you can get to almost 60 frames a second with that. If we go all the way up to 1,000 items staying put in the scene, 1,000 being created and destroyed every frame, P2 is still doing pretty well. It doesn't quite hit the 30 frames a second mark, but after some optimizations, it probably will. Gunship actually stays pretty stable. With 1,000 items in the scene, it's still 13 milliseconds, which is barely any slower than it was with one item in the scene. And if we bump this up all the way up to the 10,000 items in the scene, we'll start to see P2 actually kind of falls apart. For whatever reason, P2 seems to scale not well with total objects in the scene. However, Gunship still performs very well. With 10,000 objects in the scene, it's still in creating and destroying 1,000 objects every frame. It's only a 19 millisecond update. So if draw time, if the scene is set up well and the draw and the rendering is done efficiently, you could still hit, I think, 60 frames per second with that level of scene, which is really good. That'd be amazing. That's like that if Gunship can perform this well under actual like in game level situations, like this is still a fairly trivial test. The only thing that's happening every frame is creating and destroying cubes. That's like there's still a lot more that could be happening that Gunship might not process very well. So that's what I'll be testing in the next couple of weeks. But if it does hold up this well, that this way going forward, then I'll be very happy with it. Then that'll be a good sign for my design choices for Gunship. Now there's a third line here on the second graph, this yellow line, and if you look at the label, it specifically says Gunship with pooling. This comes from this is referring to object pooling in Gunship. And I was this week, like most of this week, P2 was outperforming Gunship, and it wasn't quite making sense to me why it was. By all rights, it seemed like Gunship should be running faster with what was going on. And I was kind of thinking about like what I was doing differently in P2 versus in Gunship, and it occurred to me that I had implemented object pooling in P2 because that seemed like a common paradigm in P2, like looking at Hector, I believe it's Hector who actually wrote the version of P2 that I have. In all of his examples, he had object pooling for all of his types, which, makes a lot of sense. If you're creating and destroying things a bunch, you want to use object pools. And I had created object pools in Gunship, but I had created them at the component level. I want to pull that up and show it to you. So I created this pooled component manager, and I do something similar I do something similar just in a different way for mesh. Actually probably be a little bit easier to just show it in mesh. So in mesh, we've got these mesh is a case where I've got ogre resources, and creating and destroying these ogre resources is expensive, but I don't have to create and destroy them. I can simply pool them for different uses. So I've got this mesh component that holds on to an ogre entity, which is effectively the way ogre does meshes. And then down here at the bottom, I've got this hash map, this std unordered map that pools up unused meshes, and it's keyed to the string value. So when you create a mesh, if we take a look at our create destroy system, we create it with you give it a string ID, in this case cube.mesh, and in our mesh manager, it first checks if for that given key, do we already have a mesh of that type, and that saves us on processing of having to create and destroy these ogre resources. And I do the same thing with the transform manager. Transforms are actually ogre scene nodes, which is how ogre constructs its scene graph. So transforms and gunships are really, again, just ogre resources. And I use the pooled component manager to ensure that I don't have to create a new scene node every time I want to create a new object with a transform, because that's another case where if I mishandle ogre's resources, it'll start to become a performance bottleneck. And so I had implemented component level pooling for objects in Gunship, and at the same time I implemented object pooling in P2, thinking those two were roughly equivalent. And it occurs to me that they're not, because in P2, when you create and destroy an object, you're calling new and calling delete to destroy, like you're like properly destroying the objects. But when you like pool up these objects, all it stays in memory as a whole chunk, and you don't have to like do any new assembly. You don't have to like reload the mesh or like recreate anything. You don't have to like re-register with a bunch of managers. And in Gunship, what I was doing was I was like still every time I was creating and destroying the cubes, I still had to like create a new transform component, create a new mesh component, and assemble those together, and then and like get it all set up, which that was a big chunk of my processing time. And it occurred to me that a more equivalent form of pooling for Gunship would be to actually pool these entire cube objects that are appearing in the scene. So I quickly threw together a very rudimentary object pool for the create destroy system. If we go to create destroy system, we'll see that we've just got this vector stack of these disabled entities. And what I do is here I've got the old code where I would completely destroy the entity. And now instead what I'm doing is I effectively disable the transform, which makes it no longer render in the scene. This is something that I don't officially support in Gunship yet. I'll have to add this functionality to Gunship to make it a little bit more ergonomic. But this is why I'm saying it's just like quick test code. But so I disable the transform so it'll no longer render, but I don't destroy the components. I don't destroy the entity. There's still live things with it. There's still live entities and components within Gunship. And then I add that entity to the list. And then every frame when I go to create the however many new cubes, I first check if I've got any pooled entities, and if I've got pooled entities, I just give it the new random position and re-enable it. And if not, I fully create the new ones. And what you're seeing here in this graph is this yellow line is actually Gunship with entity pooling enabled. And if we go all the way up to like the very, very most extreme stress test that I was running, that's creating, destroying 1,000 cubes per frame, with 10,000 cubes staying put in between frames. We'll see that with object pooling, Gunship's scene update time only takes 4 milliseconds, which is crazy good. That's really good. That's like super optimal performance, which makes me very happy. That's like exactly what I've been hoping to get out of Gunship. It's like great performance. I'm hoping that I can continue to squeeze that level of performance out of it in all of the future tests. The fact, and that brings me back to the question of P2. At this level, P2's taking, almost a third of a second to update its frame, which means that I've still got a little bit of work to do with P2. There's some bottleneck going on somewhere that I'm not fully understanding. That leads me into I want to briefly discuss what optimizations I've been doing on P2 and what work's left to do there. Actually, let me quickly check how long this video has been running. Ah, fuck, it's been running for half an hour? Wow, okay. Yeah, I'm not going to go into what I've been doing with P2. I'm gonna cut this off now because this has been going for a while. Suffice to say, I'm going to be doing a little bit more work with the create destroy test, since the create destroy test I've been spending a lot of time on because this is where I've been getting out the biggest bottlenecks within both of the engines, and I've kind of had to familiarize myself with P2 in this time. Once the create destroy test is done, I will be able to move on to some more useful benchmarks, and hopefully those won't take I won't need to spend nearly as much time doing profiling and optimization on those because I'll already have gotten the bulk of that work out of the way now. So that's what's going on. I'll next week I'll update you and see if I've gotten P2 working any better on these create destroy tests, and I'll let you know what other tests I've been running to compare the two engines. See you next week.